Welcome friend. This time we're going to be doing some experiments to discover how easy it is or difficult to heat treat aluminium castings at home in your kitchen and whether it's worth bothering with.
If you caught the last video, you will have seen me cast and make some pipe clamps. I did a T5 heat treatment of those pipe clamps, but it was only recently that I really learnt you could do such things at home in a standard kitchen oven. I was really surprised at how simple a T5 heat treatment is, so in this video I want to go into the details of how it's done and to look into the tangible differences between a heat treated part versus one that hasn't been heat treated. Now I've got Martin from Foundryman to thank for this idea, and all I'm doing here is pouring a bunch of scrap aluminium into bean can shaped round stock essentially, which I can try different machining operations on. Some of it will be heat treated, others won't. Quenching of cast parts isn't really essential, and in fact does introduce some distortion, but when I dug into it, it does seem there's consensus in the literature that straight off the bat it can increase the yield strength of the part.
Bean cans, I'm going to put one of them in the oven for about 6 hours at 160 degrees ish, and the other one I'm not going to do that with, and then we'll compare to see how they machine, how hard they are, that kind of thing. Both of them were quenched straight after they were poured, as soon as they were sort of seemed solid enough to do that without falling all apart. So we'll see. Wow, it looks pretty solid down there. We've put some WD-40 on the surface. We're getting straight in there. This is unheat treated. We're cutting at 840 RPM. Depth of cut is almost a millimeter, but then it's a varying surface. So we're straight in there. We'll give it a blitz. Seemingly successful. Well, it turned just fine. The chips, pretty nice little chips really. Yeah, little tight curls. 1050 RPM, quite a fast feed.
Those chips are looking really good. You can see the difference in finish where the WD was there. It seems like a really nice surface, certainly no visible porosity. Let's go to some edge turning. Same speed, super aggressive feed. Depth of cut 1.5 to 2 millimeters.
Struggling a bit with that.
It was asking a lot for this size of machine. Let's go to say half that depth of cut, so 1 millimeter with some WD.
Okay. Okay, well, I'll have to say I think the turning both of those was quite nice. It's a nice quality finish. I think we were coming quite close to the surface here. Let's just try knocking that off.
So at this stage in the proceedings, I've tried with WD-40, without WD-40, and I'm wondering, where is this gumminess that everyone talks about? To conclude this non-heat treated experiment, I went ahead and did a finishing pass of 0.2 millimeters.
Okay, well, I wouldn't call that necessarily gummy turning, or I just see no problem with that whatsoever.
So we'll see how that compares to the heat treated one, but this non-heat treated one turned at 1050 RPM. Seems to be pretty good. The surface finish just seems quite excellent to me. The face here was a 1mm depth of cut. This edge had a finishing pass of 0.2mm, but to be honest, it was just as good a finish at the millimeter depth of cut. It would be interesting to see how super sharp high-speed steel would finish it compared to the carbide inserts I've been using. Let's move on and look at the heat treating process. In our kitchen we have a standard fan oven and I'm running it at 180 degrees C, and those parts were in there for approximately 5 hours. Let's take a step back and talk theory for a moment. The main purpose of heat treating is to improve the mechanical properties, the strength and so on of a part, but also its machinability. That's what we've been testing so far on the lathe. What we're doing is a rough approximation of T5 heat treating, which people also call artificial aging. Aging being what seems to happen if you put something in the oven for 5 hours. Now if you pause the video and check out this table, you'll see that just water quenching will improve the strength of a part, but water quenching followed by this artificial aging process really improves the strength quite a lot. The yield strength going all the way up from 117 to 186. You will notice on the bottom row of the T5 heat treatments an even more effective regime which uses a lower temperature but for a much longer time. But unless you can get away with monopolizing the oven for 28 hours, then that's out of the question. Let's try machining our heat treated test part. For this rough cutting of the bottom we're using the same kind of speed and feed. Considering we munched and monstered that off, that's a really nice finish. Let's try a 0.2mm finishing pass.
Okay, that's a very nice finish.
Let's go for an aggressive first barrage on this edge turning. Approximately 1.5mm depth of cut. That was great. Let's try a 0.2mm finishing cut. Same speed and feed.
It's very shiny. So I can feel the difference. This one's kind of a bit more catchy on this cloth, whereas this one it just skids over. You can feel that with the fingernail as well. I thought when I turned this that it couldn't get much better, but I was obviously wrong. Okay, I did a slightly different test as well with this big block here. That was just with the power hacksaw. So that was the piece that I cut off it. I think that would definitely classify as what people call gummy. I've since heat treated this whole block, so I thought if I try taking a slice off another one and see how it cuts and check out the difference. This blade's probably due a replacement actually. So this was actually set up to run with coolant to begin with, and it's got a pump and everything, and the coolant went off this little protrusion here. I'm running it at half speed, so 30 Hertz the inverter's running off, and I just find it much more pleasant to run it at that speed. It doesn't heat up the material or the blade very much, and so cooling's not necessary, which saves a lot of mess. And although it's all set up with a tray and everything to catch the coolant and drain it down and recirculate it in the pump, it just creates a really sludgy mess. And that's amplified in a workshop like this where I'm doing woodworking and things as well. and any dust in the air really sticks to those kind of wet, gunky surfaces. All in all, I really love it as a method of cutting. As long as you're not in a super rush. You notice I don't need any hearing protection. It's just it's almost like a gentle, calming lapping of the waves. Well, hacksaw test is very interesting. Have a look at this.
I guess you would just call it gummy. There's bits that have just kind of got teared and pulled over. Unheat treated test here. And the same kind of deal. Compare that to the heat treated cut. And there's still little signs of that kind of thing here and there, but in general, much cleaner cutting. Let's just take one last glance at the chips that came off the lathe. So these are the heat treated ones, really tight curls, nice small chips, just what you want. Here's the non-heat treated ones, and certainly not terrible. Good, in fact, I would say, but not quite as nice as the others. Well, there it is, friends. Should you heat treat your parts? You tell me. You've seen the machining differences. I haven't experimentally gone into the strength differences, but I'm almost certain they will tally nicely with the literature as well. Considering how easy it is to shove some parts in your kitchen oven, I'm not quite sure why you wouldn't do it. All this assumes you are using an alloy that's amenable to heat treatment for your castings, and I certainly recommend you do. Scrap alloy wheels are a fantastic resource in this respect. Okay, I'm off to cast the rest of my pipe clamps. Stay safe and see you next time.